In our last lecture, we could not complete the discussion part. We were about to talk the non-ideal effects of MOSFET, but because of power cutoff, we had only the oral discussion. So today we will continue with that topic, and we will understand the remaining non-ideal parameters of MOSFET, as well as then we will go for the AC analysis of MOSFET circuit. So DC analysis we have already done. We have seen the voltage divider bias method for MOSFET, and we have done the DC analysis of the circuit. We have finded the Q points, and that is we have finded the operating point, and we also have drawn the DC load line. So with this prerequisite, we will now move on towards the discussion of MOSFET parameters for remaining MOSFET non-ideal parameters. Fine. So we will start with that. Let me make my screen. Okay. Can you see my screen?
Yes, ma'am.
So body effect we have learned. If you does anybody remember what was body effect? Anybody remember? Please let the lecture be interactive. Within 2 minutes, if anybody remember, please tell me. What is body effect? I told you that all these non-ideal parameters are very, very important from point of view. Yes, it is there in front of you. Do you remember body effect? Please unmute. Students, please unmute yourself. Yeah, what is it? What body effect? Picture is there in front of you. Don't you remember the body effect?
Yes, ma'am.
What is that? If you remember, please brief it. It is the slide is there in front of you. I have explained. We have explained and revised also. Yes, Piyush. Come on, quick, unmute yourself and tell me what is this body effect. If you don't know, say I don't know.
Ma'am, when a number of MOSFETs are connected,
Hmm?
then the drain of first MOSFET can be grounded, but the drain of second MOSFET also acts as the source of the first MOSFET. So, so the source to substrate voltage between.
Yes, Pejal, you got muted.
Yes, so the change in the change in the source to substrate voltage also changes the threshold value.
Very good. Very good, Pejal. Only one thing. We used to ground the source of MOSFET number one. The source substrate, the source and substrate, they are connected together for MOSFET number one, and therefore we can ground. So this is not the drain. This is the source. Okay, that only correction needed.
Yes, yes.
Very good. Very good, Pejal. I think rest of the students they are not studying at all. Okay, so in body effect, we have seen that in the MOSFET, when there are multiple MOSFETs connected in series, the the source and substrate of first MOSFET, they are connected together and it is connected to ground. Therefore, the potential, uh, but for the second MOSFET, we can't do that because the source of second MOSFET act as the drain of first MOSFET. So we cannot make the source substrate junction to be connected at the same potential. Therefore, there exists the difference between the source substrate potential at different MOSFET, and because of that, the threshold voltage also varies. Because threshold voltage, when we define for a MOSFET, that time this junction, the junction between the source and substrate, it was at ground potential. But now you will find here this is at ground, here this is at ground potential, but here it is not. So there is difference in the there is variation in the threshold voltage because of the source substrate junction of multiple MOSFET is not at the same potential. This variation of threshold voltage is called as the body effect. Then we have also seen sub-threshold conduction. Anybody other than Pejal, can anybody tell me what is sub-threshold conduction? Yes,
Current conduction in MOSFET below VTN.
very good. Current conduction below the value of threshold voltage is called as sub-threshold conduction. So we define threshold voltage is the minimum voltage at which MOSFET will start conducting. But in fact, below this voltage also there is a very small current which is flowing through the MOSFET. So this state we can't call it as a MOSFET conducting, but still there is a very small negligible current flowing through the MOSFET, right? We neglect it. But when there are multiple MOSFETs connected in the series, these small currents increases because there is small current from every MOSFET, so it generates in a sufficient amount of current that is dissipating power in the IC. Okay, so this is called as subthreshold conduction. Now we will go to our first parameter. I was explaining this in the last lecture, but because of power failure, I couldn't complete this. Simultaneously, I'll be using whiteboard. Now you know MOSFET characteristics, how it appears. Yeah. If you see the MOSFET characteristics, yeah, we have studied this MOSFET characteristics. So if you see these characteristics, you will find when on this x-axis we are showing VDS, on y-axis we are showing drain current. Okay. So this is drain current ID, and this is drain to source voltage. When we want to observe the relation between these two, we keep one parameter constant, that is VGS we keep constant. So for different value of VGC, we can observe the relation between ID and VDS. So how MOSFET behave? Consider this curve. Let's say VGS equal to 5 volt. So when you go on increasing VDS, okay, what happens? The drain current start increasing linearly. When you increase the drain to source voltage, first of all, drain current start increasing. Drain current will start increasing linearly up to this point. Okay. After that, you see there is a curvature over here. Okay. And here, in such a type of region, the inverse square law is followed. So when we go on increasing VDS, at first the current increases linearly. We call this region as ohmic region because it follows Ohm's law, because the current increases in proportional to the applied VDS. So initially the current increases, okay, and it reaches to the maximum value. It reaches to its maximum value, let's say at this point. Okay, here it becomes maximum. So I will call this voltage, let's say I will call this voltage as VDS max. Okay, at this, so not VDS max, VDS sat. Now after this, the MOSFET is entering into saturation because see, it is now remaining constant. Once it reaches to maximum, what happens there? The current is becoming constant. And when current is becoming constant, we call now MOSFET is present in the saturation region. So this region was non-saturation region or ohmic region, and this region is the saturation region. Okay, where your curve, the drain current is almost constant. Are you getting? This region is the saturation region and the drain current is almost constant. Now the point at where MOSFET is entered in the saturation, or this on this axis we are showing VDS. So value of VDS from which MOSFET is entering into saturation, we will call it as VDS sat. Okay, let's say we will call it as VDS sat, saturation voltage. So for this MOSFET, this is the saturation voltage, and after that it is entering into saturation region. Excuse me. Now if I call, this is the output characteristics of MOSFET. Okay, so can you tell me what is the expression for output resistance RO from this curve? Output resistance RO. Can anybody tell me what is the output resistance RO from this characteristics? Yes, how we define output resistance from any characteristics? What is resistance? Is the ratio of
V by R. V by
V by
I.
R. Okay, V to R. It's the ratio of V to R. So if I want to define output resistance of a MOSFET from these characteristics, so how I will define it? Which voltage and which current shall I consider in this ratio?
VDS and ID.
Very good, Pejal. So other students, please be interactive like Pejal. Okay, please. Otherwise, see, if you ask, if you reply, if you talk, if you interact, then you create a very good impression, and then I also come to know that you are attentive in the lecture. Okay, so RO is the ratio of, I can say, if I want to find the dynamic resistance, I will say change in VDS, delta VDS divided by change in ID. If I want to find the resistance at any point, then if I want to find resistance at this point, let's say, so what I will say static resistance, and I will simply define RO as value of VDS at that point divided by value of ID at this point. Okay, so I'll simply find what is value of VDS here. So whatever it is here, I will note it down, and I'll find what is value of ID on this point, and I will note it down. So I will get the resistance at a particular point, or we call it as DC resistance or static resistance. If I want to find AC resistance or dynamic resistance, I used to write change in VDS to change in ID. So at what is the change? So let's say if I am consider, so I have to consider a slope there. So let's say this is the value of VDS. Okay, now after that VDS has reached to this value. During this time, let's say ID was having this value, and now at this point ID is reached to this value. Okay, so whatever is the change, how much change has happened from this point to this point? So this value minus this value, the final value minus initial value, that much change has happened in VDS, and this much change is happened in ID. So this is my delta VDS, this is my delta VDS, and this is my delta ID. Okay, so if I find the value of this slope, if I find this delta VDS by delta ID, I get the resistance to which we call dynamic resistance. So remember difference between static and dynamic resistance. So VDS upon ID, change in VDS to change in ID is the output resistance of MOSFET. Now tell me, what is change in ID? Even though I tried to show here, you see on this curve, VDS changes from this position to this. Let's say here it is 1 volt and here it is 2 volts. So what is changed? 2 minus 1 volt is the change. But at that particular time point, if you see current, so see this graph is almost straight line. This is a horizontal, straight horizontal line. So value of ID at this point is this. Similarly, value of ID at this point is also same. Is there any change? Is there any change? Yes. Harshada, is there any change? Is there any change in the value of ID?
No, ma'am.
No, ma'am.
No, there is no change because see, current is remaining constant. So once you are increasing your VDS after saturation, even though you are increasing VDS, ID is not changing from this curve. Okay, this is the ideal curve. It means change in ID is zero. So if I note this change in ID, if I note this change in ID, I'll write here RD is equal to change in VDS upon change in ID. Of course, I have to do this for some constant value of VGS. Okay, VGS we have to keep constant. Okay, constant value of VGS. So here in our case, we have considered value of VGS as 5. You can consider any curve. Okay, so what shall I write? VRO is equal to, there is finite change, let's say 1 volt here, but ID is not changing, so change is 0. So if the denominator of this term is 0, what will be the value of RO? It will be infinite. Okay, understood? So this is ideal thing. When we say that in the saturation region, ID is constant, it means it is not changing. It means output resistance is infinite. Okay, but practically you will find that RO is not infinite and it is having some finite value. So that is why we call this as finite that is why we call this as finite output resistance. So you will observe that whatever horizontal lines we have shown, practically these are not horizontal, but there exists some slope. Okay, it means MOSFET. In the previous diagram, we have seen that once it enters in saturation, even though you change VDS, the current does not change it. Okay, but practically what happens, there is some slope. And if you extend this slope, you will find a point over here where VDS is becoming 0. At this point, how it MOSFET behaves. So here I have shown the voltage, the value of voltage at this point I am calling as VA. And it is equal to 1 by lambda minus, because it is at this side. So minus VA is equal to minus 1 by lambda. Now how this is, in short story, I will try to explain you. So to understand this, what is required to understand is channel length modulation. So let me first talk you. You know the current in the MOSFET is given by ID equal to, when it is in saturation, how much is the current? When it is present in the saturation, ID is equal to Km times VGS minus VT bracket square. Now this condition is true only, this condition is true in the saturation region. Okay, but as what we say that MOS, ideally if you see, ID also depends on VDS. ID changes with VDS also. Okay, so when this happens, now how this happens, I'm going to explain you. So in that case, the saturation current is given by Kn times Vgs minus Vt bracket square multiplied by 1 plus lambda times Vgs, where lambda is called as the channel length modulation. Now let us see where from this is. See, when this question comes, you have to write this explanation as finite output resistance. What is this? And its definition and its expression. It will be asked for 2 marks. So this the final expression is very important along with the definition. So let me explain you from where what we are showing here. So you can see these are our ideal curve. Okay, where at every VGS value you see after once MOSFET enters into saturation, the current is almost constant horizontal. Okay. This is true for this. Now come back to look at this figure. Look at this figure. You know this is your source. This is your drain. Okay. This region is source. This region is drain. This is your substrate. Okay. Now you are applying. You look at this point here. We call this voltage as VDS sat. Okay. We call this voltage as VDS sat because from this value of VDS, let's say from this value of VDS, MOSFET is entering into saturation. Okay. Here from onwards, MOSFET is entering into saturation. If you talk about the this ohmic region or non-saturation, what is happening? You increases from 0 onward, you try to increase VDS. So when your VDS becomes VT, MOSFET starts conducting, that you know. So when you apply, let's say you have applied 3 volt here, VGS value, let's say you have applied 3 volt to the VGS. Okay, and definitely it is greater than if value of VT, let's say it is 1 volt. So when you apply VGS greater than threshold voltage, it will start conducting. Okay. So from this point to saturation point, the current is increasing linearly. You know there is a depletion layer. Look, what is depletion layer? This is substrate is of P type and this is of N type. So between this, there is a depletion layer. Okay, let's say there exists a depletion layer. Okay, source and substrate, they are at the ground potential. Okay, but drain is not at the ground potential. So if you look at the junction here, this junction, the drain and substrate, if you see this junction, you are increasing VDS. बघा तुम्ही या साइडला VDS वाढत आहे. VDS, if you are increasing VDS, the reverse bias is increasing on this side. या साइडला reverse bias वाढतोय. The reverse bias is increasing at this side. Okay, see from VT onward it has started conducting. You are increasing VDS. How is your VDS? VDS is positive. Drain is connected to positive. Okay, when N region is connected to positive, it means you are increasing the reverse bias. So when you increase reverse bias, suppose initially this was your channel form. हा तुमचा channel आधी form झाला होता. Initially this was the channel form, but then you are increasing VDS. So what is happening? The depletion layer at this side is increasing. So it will then become like this. Okay, it will increase. You can see the green color portion here, black color portion here. So depletion layer is increasing. So when depletion layer increases, channel width decreases. So initially, suppose this was your channel. This was your complete channel. Okay. But when you have started increasing VDS, the depletion layer has started increasing. Therefore, on the right hand side, that is near the drain, the width of the channel is reducing. So your channel is reducing here. Okay, it will become first like this, then it will become like this. Again, if you are increasing, it will become like this, and it will become like this. What is happening? The channel width is decreasing near the drain. You can observe that this channel is wider here and it is very smaller here. Okay. So increase of the drain current with increase in VDS is happening till this condition. After this condition, still if you go on increasing, काय होणार? And this effect is now called as we are calling this effect as a pinch off effect. Okay, the channel is becoming narrower and narrower and narrower near the drain, and one stage will come that the channel will simply here it will touch to a single point. So what is happening now? The current now pinch off of the channel is taking place. The channel is pinched off. Okay, and therefore only a constant current is entering here. So at this point when the channel is pinched off, this current becomes constant. Okay, and we said now the MOSFET has been entered in the saturation. So till that point the current has increased, but after this point pinched off is happened and the current is becoming constant. Now if I ask you, you go in reverse direction. You have increased voltage till this point. Are you getting? You are increasing the voltage. If somebody asks you decrease it, then what will happen? Again the channel will become little wider here. Channel थोडा मोठा होईल इथे. कधी जर केलं तर तुम्ही अगदी VT एवढं केलं तर channel असा होईल. Complete, right? So it means when you are changing VDS, your channel width is changing. Okay, agreed? Are you getting? In this
Yes,
region,
ma'am.
good. When you are increasing VDS, your current is increasing simultaneously. Because of increase in the VDS, the channel length is decreasing near. Sorry, the channel width is decreasing near the drain. Drain current, I will say, yeah, that the channel length is decreasing near the drain. And then MOSFET enters into the channel is pinched off. Once channel is pinched off, constant current will flow, and we say MOSFET is entered in the saturation. Now look at the next slide. Look at this slide. Further, if you increase, you will find the point which I have shown here. It will move here. Okay. जर तुम्ही जास्त आणखी VDS वाढवलं तर इथला जो चॅनल आहे हा जवळपास 0 होईल. Okay, so in that case, first of all, your channel was touching here. So I say this is the effective length of the channel. इथपर्यंत हा channel चा. If you further increase the channel, this point will get shifted here, and I will now say that this is, I will call this length as a delta L. So if the point is moved here, I will call the effective length is L minus delta L. L is the length of the channel previously, but because of change in this, see, the width of the length of the channel is changing due to applied VDS. So this phenomena is called a channel length modulation. जसं तुम्ही VDS change करता, channel ची length सुद्धा change होते. Effective current conduction ची जो channel form झाला त्याची length change होते. So we call this as channel length modulation. So if this is your value, length of the channel, and because of increase in VDS, this point will move away, जिथे तुमचं pinch off होता है, and therefore I will say this length is now L minus delta L. It means the channel length modulation is happening. So what we say that ID is equal to VGS minus VT bracket square. ID equal to K times VGS minus VT bracket square. Okay, where your K is nothing but this. This is your K. 1 upon 2 mu n into COX into W by L ratio. Okay. So this is true up to here. But now This is true up to here. I have only written the value of k here. So this equation is true up when this is the point touching here. But still, if this point shift here, still if you go on increasing VDS, this point will be shifted here, and therefore channel length will also increase. So this L, the value of L is going to increase. Value of L is going to increase. Okay. So I will change this L by L minus delta L. Our new effective L is L minus delta. Don't worry about the equation. You are not supposed to derive this equation, but I am explaining this so that you will understand what is happening actually. Okay, so from the formula of ideal saturation region, we will change the value of value of L to L minus delta L. Okay, now L minus delta L can also be written like this, and if you further solve this, okay, uh, so if you further solve this, you can write 1 minus delta L bracket raised to minus 1 as 1 plus delta L. How? Because you have studied the expansion of the series 1 minus x raised to minus 1. That is 1 upon 1 minus x. So we can write this 1 minus delta L by L. If you consider this as a x, and if I solve this series, I can interpret this series as 1 plus x. Okay. So I can write this 1 minus delta L by L as 1 plus delta L by L. Okay. 1 plus delta L by L. So in this, I have to put in the equation, because now my channel length is varying. So I will multiply ID by this term. And this is further, this change in the length, this delta L, it depends on the how you are varying VDS. So we will write, because delta is proportional to VDS, I will write this delta L by L as a lambda dot delta. Means it is a function of VDS. Okay. So I will write this as lambda dot delta L. The lambda का है, it's called as modulation parameter. In short story, I wish to tell you that the current in the saturation region is given by this equation, that is ID equal to K times VGS minus VT bracket square. But this K is dependent on length also. Okay. So at this point, when you are increasing VDS, the pinch off point gets shifted here. It means the total length of the channel is also changing, right? Total length of channel is changing. Therefore, the current does not remain the same as what we have written, but it becomes the function of a parameter. It becomes the function of a parameter called as lambda, which is known as channel length modulation. So we say this is our ID, which we have defined for saturation region. But because your VDS is dependent, because your ID is also dependent on current, and it varies due to channel length modulation, this current gets multiplied by a factor called as 1 plus lambda delta VDS, 1 plus lambda into VDS. So you remember this. How this came, I told you. So the current becomes the function of 1 plus lambda times VDS. Now I'll show you where is this. Look at this figure now. So whatever we say that the MOSFET characteristic, the drain current is constant in saturation. So practically it is not constant, but it is having some slope, and this arises due to channel length modulation. So if you extend Check it right for me. So the new ID, the new equation for drain current, it becomes the old equation ID gets multiplied by 1 plus lambda times VDS. So from the last characteristic, we concluded that RO is equal to delta VDS upon delta ID. And our delta ID was not varying, it was 0. So we said it is infinite. But now delta ID is varying by a small amount. So it cannot be treated as 0. So what is our new ID? We call that new ID as ID dash. So ID dash is equal to old ID, that is ID in saturation multiplied by 1 plus lambda s. Now if you want to calculate resistance, so it will be, what is resistance? VDS upon ID. Okay. Or I can write 1 by RO. Here I have written 1 by RO, inverse of resistance, as ID by VDS. Okay. So that is equal to lambda times ID. So RO is equal to 1 upon lambda ID. If this is 1 by RO. So ID is not constant, exactly horizontal, but it has slope. So if you exceed this slope in this direction, here there is a point where it is touching that VDS is equal to 0. I will call this voltage as VA. It is same as early voltage of a transistor if you have studied in first year, I don't know. This is called as VA. So at this point, I told you that your pinch off point is moving and it becomes the function of lambda. So this VA is equal to 1 by lambda. Okay. So if you want to find RO, it is shift, power switch off. Please wait, it is on.